Hey guys, this is Ron. This is Lab 14, which covers spanning tree. Okay, spanning tree is a pretty cool little tool that enables you to add some redundancy in your network without creating some switching loops. So in our case, I've got these extra 2 links right here to provide some redundancy. However, if we didn't have spanning tree running, what would happen if a broadcast hit this switch? That broadcast is going to get sent back out on every port except the one that it came in on. What that means is that broadcast could go this way, this way, this way, and then right back to it. And what happens then is it's going to be sent out again. All right. So as broadcasts continue to hit your network, they're just going to continue to kind of go through this loop over and over and over and over again. And what you're going to see on your switch is that every light is going to start blinking incredibly fast to the point of you think this thing might explode. All right. From your user perspective, they're going to see the network start to get really sluggish. And eventually, if it gets bad enough, they're not going to send any traffic, because your network is just being pounded by all these broadcasts. So to stop that from happening, we either design our network without any redundancy so that there's no way that there could possibly be a loop, or we implement spanning tree. So in my case, we did spanning tree so that I could add these links. That way, in case one of these links for some reason fails, somebody cuts a cable in the building, if some fiber gets torn up, you name it, I've got something built in so that I still have an alternate kind of route out. All right. So if I jump on one of these switches, we'll look at it real quick. So it's show spanning tree, and here we see this bridge ID. Okay, so the bridge ID is going to be made up of a priority and a MAC address. Okay, and the MAC address, it's not something new that we haven't already seen. I mean, all these network devices, they all have MAC addresses. The bridge protocol or bridge priority is something slightly different. By default, it's 32.768, but then we add in the VLAN ID or VLAN number that we're working with. Spanning tree works on a per VLAN basis. So I'm running just VLAN 1, so the priority ends up coming to 32.769. Okay, so what we end up doing is when the switch comes up, it sends what's called a bridge protocol data unit, a Bpdu. Okay, and this Bpdu contains its bridge ID, which again is the combination of priority and MAC address. And it's as each switch gets these Bpdus in, it's going to compare it against its own, and it's going to say, is this one have a higher bridge ID or a lower bridge ID than me? Okay. Now in the spanning tree world, lower is better, meaning the lowest bridge ID ends up becoming the root ID. And the root ID ends up being a central point in the network that everybody maps to. So let's say he becomes the root ID. Everybody is going to evaluate their ports based upon its path back to the root. Okay, so I'm going to say to get back to this root, I could use this port or I could use this port. And then it's going to evaluate them. So if I come back up to here, that's what he's done down here. I'm going to take each one of my links and give it a cost, and that cost is based upon the bandwidth of the link. So this is a fast Ethernet link, so I give it a cost of 19. Gigabit Ethernet, which is faster, has more bandwidth, gets a lower cost, because again, lower is better in the spanning tree world. So what I'm going to do is I'm going to add up all the costs. So I could go this route, and that was the fast Ether port. So this path to my root has a cost of 19, but if I go out my gig ports, then I've got to go 4 plus 19, because that's the path to get back to the root. So this fast Ether port, even though it initially has the higher cost, overall it has the lower cost, and so it becomes the root port. All right, and that root port is always forwarding and it's in the direction of that root bridge. The rest of my ports become either designated ports or non-designated ports. Okay? In my case, both of mine are left as designated ports, and they're forwarding. Okay? Now, if we come down here and run the same thing on him, show spanning tree, you'll notice that I have designated ports. I have my root port, but I have this ALTN port, or maybe alternate port. Really, this is the non-designated port, and it's in a blocking state. So what made this one a non-designating and the rest of these as a designating? Well, a couple of things happen. Again, we're trading these BPDUs, and in my case, I left the priorities all the same, so they all have the same priority, which means we're just going to compare it against MAC addresses. So I know that this is a gig port, this is a gig port, so that's 4, and then this is a these are those 19s, those fast Ethernet ports. So each one has the same value as my other ports. So I have to choose which one is the best port. So I've now determined the costs are equal. Well, what about the bridge IDs? Okay, so I come and look. Okay, 0060, 0050. So he has the lower MAC address. So he becomes the root port, and this one becomes a designated port. But then when I compare it, my MAC address, 3 Echo 9 Bravo, 3 Echo 55, he has the lower address. So I shut my port down, and he keeps his port up. Okay? So I have to disable one of them so that I don't create a loop. But determining which one gets cut is first, okay, this is the better port because this one has the lower MAC address. So I know I'm going to shut this link down. So now I just have to determine, well, who shuts down their side? Well, I have the higher bridge ID, so I shut my side down. Okay, and that's all that happened down here. We said this is 4 plus 19 plus 19, so the costs are the same, but I know I have to shut one of them down because I've got a loop here. So now I compare my MAC address with his MAC address. I've got the higher address. I shut down. All right. And when I looked at my two places to go, he has the lower MAC address. So instead of going to him, I go to him. All right. And so in doing that, I determine which side of my link goes down, which one of my links goes down, and how do I get to that root bridge. Now in my case, this guy had the lowest MAC address, so he became the root bridge. But what would happen if one of the switches down here had a lower MAC address? Or even if a switch down here got a lower MAC address? You run into some problems that if one of these guys becomes the root bridge, everybody else is going to map the network back to him. And what you don't want is they're going from one side of the network all the way across the network to get to him, because it's going to make my network run inefficiently. So what you want is the center of your network to be that root bridge. Okay? So we call this the access layer. We call this the distribution layer, and this the core layer. So you want your core layer to end up being the bridge or the root bridge. All right, and to do that, we're going to change those priorities to make sure this guy has the lowest priority, this layer has the next lowest priority, and then your access layers have the highest priority. Okay. So when we come in here, all we're going to do is enable config T spanning tree. And if I do a question mark, we have VLAN because we're doing it on a per VLAN basis. So VLAN 1, because that's the VLAN I'm using. Now I can do priority, and I can assign it an actual priority. The only snafu is that it has to be an increment of 4096. So in my case, I'm just going to give it a bridge priority of 0. All right. So end. I'm going to write to save it. I'm going to come down here to these guys. Fig T, spanning tree. This is VLAN 1 priority 4096. So now, if for some reason my root bridge fails and goes down, this is the next layer, and these guys are gonna become the new root bridge. All right. So spanning tree, VLAN 1 priority, and I'm gonna make it 4096. All right, so we're good there. All right, now, so we've gotten spanning tree set up. It's running. It's doing everything it's supposed to do. The only problem is, and what you'll see, I'm going to go ahead and power cycle my devices, is you're going to find when the switches finally get through their initial boot up, when spanning tree kicks in, there's a period of time where they're not sending any traffic. So notice up here, everything is red, but everything down here is green. And the reason for that is up here, I'm just letting spanning tree do what it's designed to do. It has started sending out BPDUs. It's elected a root bridge. It's evaluating its ports based on how to get to that bridge. It's deciding which ones are designated and non-designated ports. But really what's slowing it down, because all of that happens pretty quickly, is this listening, learning, and then forwarding process. So initially it's going to come up in listening, okay? And in listening mode, it takes in the BPDUs from other switches. It looks over it, compares it against its own, but what it doesn't do is it doesn't take the MAC address out of that BPDU and add it to its MAC address table saying, oh, I know how to get to that switch, or I know how to get to that user. It came in on this port. All right. So it'll do that for a period of time, and it's something like 20 seconds. Then it'll go into learning mode, and in learning mode, it continues to look at those BPDUs, and then it also starts to populate its MAC address table. So now it starts filling in that MAC address table, learning where people are on the network, so that when it finally gets to forwarding after 20 more seconds, it has a partially filled MAC address table that it can start to filter on. All right. So by the time it does listening, learning, and then gets to forwarding, you could be looking at 50 seconds for your network to converge. So if you take a power hit for some reason, you got to wait for the switch to reboot, and then you've got to wait for almost another minute for spanning tree to start passing traffic. All right. And in some cases where you have users like computers, servers, what have it, sometimes being down for that long can cause issues, with their network card or with their DHCP or what have it. Just being down that long can cause issues. So what you can do is turn on something called port fast. And I have done that on this bottom. Okay, and all I did to enable that, so enable config T interface FA01, because that's one of the ports that I enabled it on. Now you can do a range here, which I do all the time. And then you just do a spanning tree port fast. All right, and it gives you a little warning. Hey, you only enable port fast on stuff that's connected to a single host. Please do not use it on hub, concentrators, switches, bridges, blah, blah, blah. All right, so what we've done is we've told it, you know what, don't go through that whole learning, or listening, learning, forwarding kind of thing. Just go straight to forwarding. Ignore all that kind of other stuff. So it'll speed up how fast this comes up. But the problem is what happens if somebody comes in behind you, not realizing that you've turned on port fast, and they connect up another switch out here, connect it to your port, and then it ends up connecting back into the network. You've created a loop. You turned on port fast, so it's going to ignore all the rest of those BPDU stuff, and you're going to have issues. Well, Cisco came up with a couple proprietary methods for helping you out so that you can still use portfast, but you don't open up yourself to the risk of creating loops. And they do that with Bpdu Guard and Bpdu Filter. Now, I'm not going to show it too much here because, well, I guess I could do spanning tree, question mark. They've got Bpdu Guard in here. And Bpdu Filter should be in here as well, except this is packet tracer, so it's limited to what commands I can actually run. What this is going to do for me with Bpdu Guard, I have enabled portfast, but if a Bpdu comes in on that port, the port's just going to go into error disabled state. It's basically going to shut itself down because it sensed that another switch was hooked to it, and you already told it that you weren't going to hook a switch up. So to eliminate the possibility of a loop occurring, it goes into error disabled state and kind of shuts down, basically. Now, Bpdu Filter does the same thing, except it's a little bit nicer to you. Instead of error disabling the port after getting a Bpdu in, it just turns off portfast. Okay, so you turned it on because you were telling it that you were only going to hook to a single host. Somehow a switch got hooked to it, so it just goes in and turns off portfast. So spanning tree rules will come back into play, and you should still be safe. Okay. Now again, those are Cisco proprietary. There's also another two things called Uplink fast and backbone fast. All right. And I've never enabled these personally, but what they're there for is you're planning for a network failure. The reason you put redundancy in a network is because you're planning for a network failure, right? So what Uplink fast and backbone fast does is allows the switch to also plan for that network failure. So Uplink fast will get enabled at the access layer, whereas backbone fast will get enabled on the entire switched network, so all of your switches. Okay, Uplink fast just at the access layer, and it says, okay, I've got multiple paths back to the root, right? But I'm only using one of them, so I'm going to keep in the back of my mind these other paths. So if my primary fails, I'm just going to very quickly jump over to what's remaining, to a path I know that still goes to the root. If you didn't have that, well, you're going to have to reconverge, and then you're going back through the whole process of listening, learning, all that kind of stuff. So the convergence time, it can kind of save you almost 20 seconds in reconverging, right? Or 20 seconds might be wrong, but it's just going to save you that time that you would have to go through had you not turned it on. So that does it at the access layer, and it's for local failures. What backbone fast does is it allows you to sense that a link failed on another switch and plan accordingly. And it does this through something called, let me look it up here, inferior BPDUs. Okay, I had to read that one because, again, I've never personally used it. And what this does is, if, let's say, a switch loses its link to the root, sometimes it will elect itself as the new root, and when it sends out a BPDU to this switch that has a link back to the root, it's going to look at that BPDU and say, wait a second, you're calling yourself the root, even though I know the root is this person. So in that way, it kind of learns about, okay, there was a failure over here, and it kind of plans accordingly. Okay, I know it's a weird way to explain it, but again, my experience with it is somewhat limited. Now, lastly, the one last thing I'd like to talk about. So we're running what's called per VLAN spanning tree, PVST. All right, and it can take almost 50 seconds for the network to get that initial convergence. You know, well, there's also something called rapid spanning tree protocol. All right, it's non-proprietary. I think it's 802.1 whiskey, and it's going to save you a lot of time on that convergence. It's backwards compatible with 802.1d, so there shouldn't be too big of a scare in enabling it. So if I come to my root bridge here, do a config T, I'm going to do spanning tree, question mark. Now I got this mode. Now PVST is what we're currently running. And if I'll do a do show spanning tree, and if you notice up here, spanning tree enabled protocol IEEE. So this is the original specification of spanning tree, the 802.1d. Alright, well if I do a spanning tree mode rapid PVST, I enable that. Now I do a do show spanning tree. Notice up here now, spanning tree enabled protocol RSTP. So now I'm running the rapid spanning tree protocol. And I'm going to go ahead and write it. And I'm going to enable it on these two switches as well. Spanning tree mode rapid PVST. And write. What we should see is those devices, or those bridges running rapid spanning tree, should converge a lot faster. So spanning tree mode rapid PVST and write. Let's go ahead and power cycle. I'm going to go ahead and reset it. What we should see is that the top half, again, should converge a lot faster. This is just, while this is powering up, I'll just let you know. So we had a couple modes before. We had blocking, we had forwarding, we had listening, we had learning, and we had disabled if you have an actual port disabled. Okay, so if you notice, the top has already converged and the bottom is still converging. Okay. Now instead of having those 5 modes, we have discarding, learning, and forwarding. So it becomes a slightly simpler process. And if you notice, now it's finally converged down here. So rapid spanning tree converged a whole lot faster than just the PVST. So this is the original specification. This is the newer kind of stuff. And again, this is non-proprietary, so you should be able to run it on most vendors' switches. Okay, so that's pretty much it for Lab 14. I hope you got something out of it. Spanning tree is pretty cool. Helps out your switched networks. Allows you to add some redundancy without accidentally creating loops that will take down your network. But it's really not too difficult. Again, the things that I would try to get out of it is BPDUs are going to get sent by all switches. A root bridge is going to be found. You want to make sure you specify who that root bridge is, and you do that through the priority. So we did that at the core layer. Down here at our access layer, I ended up turning on port fast because it helps out my users. But then in turning on port fast, we want to either use Bpdu Guard or Bpdu Filter so that we don't accidentally turn on, accidentally create a loop. And then if you can, go ahead and do rapid spanning tree instead of the original spanning tree because it converges a whole lot faster. So thanks for watching. Again, hope you got something out of it.